I am glad to introduce our speaker today. It is Ricardo Trindade, and his talk is titled Towards Micropaleomagnetism, Coupling, Nanotomography, Micromagnetic Modeling, and Magnetic Microscopy.
Okay, so first, I'd like to thank you for the opportunity to talk here. The idea of this talk today is to say a little bit of what we are doing as a group. And that's why I've put lots of other people here that contributed to specifically this topic. I have Wallison Bellone, which was a former PhD, is now in Wayne Williams' lab in Edinburgh. Gelson Souza Jr., which is now in Harvard, working with Roger Fu. Leonardo Ieda is a colleague from the University of São Paulo working on inversion of magnetic results of magnetic maps. And Thales Pescarini is another PhD student. He spent 1 year in Yale's lab working on remagnetized carbonates. So the idea of the talk today is to talk a little bit about all those advances that we have done as a group, trying to go from the bulk rock classical paleomagnetism to more grain-focused paleomagnetism using some advanced techniques of nanoimaging, micromagnetic modeling, and also some inversion of magnetic microscopy. So the layout of the talk would be from bulk rock to single grain paleomagnetism. So what we want to do. Then we are going to talk about single grains characterization. How many grains do we need to do this paleomagnetism based on very small samples? And then paleomagnetism in the microscope. So as all you know, what we do is paleomagnetism nowadays is we go to the field, we collect samples, we orient the samples. Here I have a colleague working on some dikes in the Amazon. Then we have this the dike, the sample, the cylinder collected. Then we extract the cylinder. Then we go to the lab, we cut them into several different small samples. They're very important for the statistics of the paleomagnetic measurements. We need several samples from the same site, but also several sites to account for the secular variation of the magnetic field. Then we go to the lab and we measure all those samples, and we obtain, after all this, a paleomagnetic direction, a characteristic direction, and eventually a paleomagnetic pole. All that also in parallel being based on a very careful evaluation of the magnetic mineralogy of the rock. So we do this all based on bulk rock measurements. That's the basis of eventually everything we do. But early in 2007, there is this paper by Ben Weiss and his group already showing that it's possible to do paleomagnetic analysis using magnetic microscopy, going from the bulk rock to the single grains or groups of grains analysis based on magnetic maps. After this paper, lots of other studies were done trying to investigate the paleomagnetism from this perspective of magnetic imaging. And I would say, and then it's important to mention all the works that have been done by Richard Harrison's group, by Leonard de Groot, by Roger Fu, a colleague that has collaborated with us in the past years. So several different groups are trying to move forward the domain to from the bulk rock to the analysis of single grains or magnetic imaging in this past decade or so. We decided to also start doing something in this field, and we studied at first. We started this study of microanalysis and nanoanalysis in a special group of rocks. We decided to study remagnetized carbonates. We have in Brazil and in also Western Africa a large group of neoproterozoic carbonates. Those rocks, they are spread all over the central part of Western Gondwana. They were formed, they were deposited and in the Diacaran, but all those rocks, they suffered a very large remagnetization event at the end of at the end of the Neoproterozoic, or even in earlier times in the Ordovician. We have a large group of formations covering around 4 different shields, and all those carbonates, they were remagnetized more or less at the same time in a large event of remagnetization covering the Neoproterozoic. Those rocks, they have a very complex magnetic mineralogy, but they are also they have also very stable magnetic mineralogy. So that's why we are interested at first to study those rocks and investigate those different minerals at the grain scale. So if we go for the bulk characterization of those rocks, we have the typical magnetic fingerprints of remagnetization. One of them is constricted hysteresis. All of them, they have those anomalous hysteresis loops in the form of wasp-waisted or some belly hysteresis. That's for all the units that we have studied. They fall between the considered to be the trend for remagnetized carbonates here at the top, and the trend for non-remagnetized carbonates, as previously it has been shown by other authors that those trends, they are really not always valid for remagnetized carbonates. We can have non-positive fingerprints for those carbonates, but our carbonates, they fall between what we expect for remagnetized carbonates and those that are non-remagnetized carbonates as well. They have also typically a very high frequency-dependent susceptibility, showing that there are several superparamagnetic particles in those carbonates as well. From scanning electron microscopy, we can have pyrrhotite and also clays, and that the iron minerals are very strongly correlated to the clays in those rocks. We see from low temperature measurements that we have typically the Besnus transition showing the presence of those pyrrhotites. We have also very transitions showing the presence of magnetite. From ERDA and ACM, we also see that we have iron oxides. Those iron oxides are very closely related to smectite, and from the smectite elite conversion. So we have here typically on the right an iron oxide inside an agglomerate of clays. And here, down here, we have a typical clay fragment containing smectite, but the central part is elite, converted to elite, and also connected to the presence of iron oxide. This reaction has been, from the conversion of smectite to elite, has been considered one of the candidates for the mechanisms for the formation of new magnetic grains and the remagnetization of carbonates at large scale. It requires heating. It requires eventually only the burial of the sediments, the carbonates, and the clays to provide those iron grains. Then we started to think of studying those grains at very high resolution, but then using a platform that is a synchrotron measurement platform to explore those compositions at very high resolution. This is a measurement of XANES and XAFs, in which we can have the composition of those grains, and we can confirm the presence of pyrrhotite and magnetite or magnemite, given the spectra of the XANES and XAFs spectra that we have obtained in those grains from the synchrotron measurements. So it means that we can obtain from synchrotron measurements information that complement the bulk rock properties, but at a grain level, at a very high spatial resolution. So we have in those carbonates in particular, pyrrhotite plus superparamagnetic grains plus single vortex magnetite. We have constricted hysteresis, and we have magnetite-like form due to bismagmatite light conversion. We have also a complex magnetic history in terms of magnetization and remagnetization, always with two components of magnetization, one viscose, another one related to thermoviscose on pyrrhotite and magnetite. So we believe that the remagnetization of those rocks is related to the pulse-orogenic cooling. And what can we learn from non-conventional techniques in those rocks? We are very lucky here in São Paulo because we have a large synchrotron facility very close to home. It's about 50 kilometers from our university. It's nowadays is the brightest light source in the world. It's a 3 giga electron volt source of light with nowadays 10 beam lines currently working for proposals, and we have about 8 new lines being commissioned in the next years. And those lines, they allow us to do several different measurements for the micro and nano characterization of particles. And the synchrotron in Brazil, it accepts also proposals from different domains of knowledge from all over the world. So anyone can ask a time in the Brazilian series for analysis. So one of the things that we started to do, and we are working now closely with them to develop, is ptychography or ptychographic X-ray nanotomography. This is part of the thesis of Wallison Bellon, working on those carbonates I was talking about. Using the technique of ptychographic X-ray nanotomography, he was able to map some hundreds of particles inside a small volume of about 18 micrometers to 36 micrometers high, this pillar. This is the sample that was eroded from the sample, a regular sample in paleomagnetism. And so this small sample provided at the tip of the sample about 130 or 140 small particles of iron oxides. Here at the top, we see a sample with separation. This separation is made by the density, electronic density of those materials. We have iron oxides separated from phyllosilicates that are shown in yellow. The gray background is the carbonate, and also we have some hydrocarbon in green. Here at the bottom, we have all the iron oxides shown in dark red. So all those particles are natural particles that are related to the different phases of magnetization in this rock. From this ptychographic X-ray nanotomography, you can also have this grain size distribution of those rocks. So you can see that we have, here's the size of the long axis and the amount of particles. We have the particles, most of them below 1 micrometer. Actual ratios are below 3 usually, but mostly below 2. We have also, can also define the shape parameter of those particles. We have mostly prolate grains, but some oblate grains, but they are distributed around neutral shape parameter. And then having the shape of those grains, we can do micromagnetic modeling. For that, is also part of the Wallison's thesis. We used in collaboration with Professor Wayne Williams, the MERRILL micromagnetic modeling routine. The idea was to obtain the variation of properties of those particles at grain scale. So this is just to give you an idea of 2 examples of the more than 100 grains that were modeled. We have a single domain grain here at the top, and here at the bottom we have a vortex state grain. Most of the grains that were imaged, they are between the single domain and vortex state. We have some grains that multi-vortex and some very few grains that are falling the domain of multi-domain grains. This explains also why those rocks, they provide such a very stable magnetic result. Based on all the measurements we have done, all the modeling that was done, we were also able to model the hysteresis that we have, the inversion of all grains that we modeled from that small pillar. When compared to the bulk measurement of hysteresis, provides a mixing between several different contents that were observed from the images and also from the micromagnetic modeling. We can show that 58% of the hysteresis signal can be modeled by a single vortex magnetite. Then we are left with 21% of the signal that must be modeled by pyrrhotite, and 21% more that is related to the superparamagnetic particles. So this, the comparison between our bulk measurements with the measurements that are done using the nanoscale and microscale observations allow us to give us a more quantitative assessment of the mineralogy that we have in our rocks. Then we also show that there are some grains that are very stable, and this has also been shown by several other colleagues, mostly working on more predefined shape for the grains, showing that there are grains that are very stable. They are stable at the scale of the time and the duration, the age of the solar system. In this case, we have some of those very stable grains also modeled. This is a typical one, showing that there's only a common state for throughout the whole range of temperatures. But we have also some grains that are very stable, in which we can assume different states throughout the temperature spectrum, and those grains can fail typical thermal experiments, for example, for paleointensity. Then we also were interested in knowing about the unstable magnetic zone of real grains. In a seminal paper by Nagy in 2017, together with the group of Professor Wayne Williams, he has shown that there is a narrow band of granulometry or grain size in which the grains are typically unstable. In here we have tested this with several different grains with different shapes, different sizes, and we see that a very minor proportion of our grains fall in the unstable magnetic zone. The other thing that is interesting for us, and this is something that we are also working on, is that if those assemblies that we are detecting through nanotomography, if they are detectable through magnetic microscopy. This is the work of Galson Souza. Galson is working on inversion methods using QDM measurements for to obtain the full vector of the grains inside the sample. So this is the pillar that was measured by Wallace in the synchrotron here at the top. Here we have a simulation of the magnetization provided by those grains. If we measure at the top of the pillar with the QDM. And on the right, we have the estimation of the location of those sources that is made automatically by this algorithm. And then the magnetic directions estimated using the Gelson's software. To obtain the location of the sources, what Gelson has done in his work is to use a technique that is very common in aeromagnetic surveys. It's called Euler deconvolution. So the Euler deconvolution technique doesn't need any other a priori information except the magnetic map itself. And then based on the magnetic map, this technique is able to find the X, Y, and Z location of the grains in a very robust way. And this information is then used in the inversion of the magnetic moment of the particles from the magnetic microscopy results. So the question is if those assemblies are detectable through magnetic microscopy. Yes, they are. And the important thing about this is that if we can then obtain the information of the full vector from each grain, now we are able to go forward and analyze each grain or grain population individually, and then do measurements from different populations from the same thing section or the same field of view in the case of the QDMs. So this provides a very nice perspective for the analysis of individual grains, providing different populations that can eventually be related to different magnetic events or different geological events. This also provides a possibility for us for the development of no-hitting methods, because the separation of the components can be done spatially and not necessarily now based on the thermal or the coercivity spectra. And this is also very important because we are now going to study very special and small samples that are supposed to be recovered in space missions, but also from other kinds of expeditions and missions. Something important to now talk about is how small, how big is this sample? How many grains we need to provide an average of the magnetic field? In a paper in 2017, Berndt and co-authors suggested that we need an amount of millions of particles to provide a statistically robust orientation. We have, using the single vortex models, we have restudied this aspect, and this is a result that we have now a paper under review. It has passed the first evaluation phase. And what we have done in this paper is to obtain from the micromagnetic modeling a group of a number n of particles going up to thousands of particles. We simulated the acquisition of thermal remanence in those particles from 0.1 microteslas up to 50 microteslas. And then we investigated what was the dispersion or the average angular misfit between the expected direction and the direction provided by the mean direction of those grains. And here we have at the upper panel the angular misfit, and then the number of particles. And what we see is that for magnetic fields in the range of the magnetic fields of the Earth, a small number of particles at the hundreds is already enough to provide a magnetic direction with angular misfit that is below 5 degrees. The same thing we can see here at the lower panel, showing the average magnetic moment and also the sensitivity of different equipment we have, and the intensity of the field through time along the axis, the x-axis, and the amount of grains from 2 grains to 10,000 grains. So it shows us that depending on the magnetic field that induced the remanent magnetization, an amount of hundreds of thousands of grains is already enough for us to provide a reliable results that can be measured by the equipment we have at hand. And this now is an example of what we can do. Here we have 2 different samples that are under that Gelson is studying for his PhD. This is, in the left, we have a ceramic sample from an archaeological site that was already studied for arc intensity. And on the hand side, I have a basaltic sample showing a phenocryst in the middle of the image with ferromagnetic inclusions in it. So we have the matrix with lots of anomalies related to different magnetic grains, but also the center of the image, we have this phenocryst with some inclusions also showing some magnetic signal. In the case of the ceramics, we have much less magnetic particles, and we see this from the magnetic map, but those small dipoles, they show the presence of particles that are also in those small blobs here that's related to some heterogeneities in the ceramics, but also in the matrix of the ceramics. I'll show the results only for the basaltic sample for shortness. So when we see the basaltic sample, here we have the angular misfit. Here's 10 degrees. Here's the number of particles. We were able to image from that basaltic sample about 7,292 samples. The inversion of the whole image takes some minutes only. And then we can start to see how many grains or how many grains are necessary for us to provide a direction that is very close to the expected direction that was imparted into the basaltic sample. So we have here in red a method of inversion that is based on Euler deconvolution but not iterative. And then a new method that Gelson is now developing, and he's soon submitting the paper for publication, using an iterative method to obtain the position of each particle and then invert for the magnetic moment. And we see that there is a very nice match from from the hundreds of particles, from several hundreds of particles to thousands of particles, we have a perfect match between the expected direction and the average direction of those grains. But very fast, they converge to a direction that is exactly the direction that was imparted into the rock. That's what I had to show, and I'm open to questions and to talk about this advances in the micropaleomagnetism.
Okay, Ricardo, thank you very much. We will give a big clap to Ricardo. Very, very nice presentation. Thank you. Now we open the microphone for anyone in the audience make questions. I do have one question in the chat from Gabriela Lobo. I think she's not here anymore. I can read it. Gabriela, do you want to read it or? Okay, I'll read it. She says, thank you very much for your presentation. And she asks, why did ptychographic X-ray nanotomography was chosen instead of synchrotron-computer tomography? Is the resolution better?
It's the spatial resolution. It's completely different. For CT scan, you can go down to usually 1 micron, whereas for ptychography, you can go down to a voxel size of some tens of nanometers. So there's a big difference between CT microscan and ptychography. The other technique that can reveal ptychography is FIB, SEM, slice and view. There's a technique using the focused ion beam that can also, through the erosion of several surfaces into a sample, to provide a three-dimensional reconstruction of the grains. So that's another possibility as well. That has been used by Harrison's group in some papers.
Okay, she says thank you. Williams?
More of a comment, really. Hi, Ricardo. Very nice talk. I missed the first few minutes, I'm afraid. But so the comment is just this recent paper by Gelson, that's almost published.
Yes.
I think that combined with the QDM work really does open the possibility of doing, real paleomagnetism on these very small, thin sections. And I know Gelson's working towards that, as you are. And I think the ability then to invert just a few thousand, I think it should be possible, and really get some paleointensity intensity estimates. It'd be amazing to see actually what we can get from those samples. So I've no questions, just a comment.
Yeah, I just add to this comment that the partnership with WIND has been very, very important for this to advance. It's amazing what the MERRILL can do, and all the things that we are doing with MERRILL. There's something that I didn't mention, is that we are also working on data sets based on the micromagnetic modeling to evaluate all the different inversion methods for magnetic microscopy. So this is also something that Gelson is working together with Wynn and Wallison. So we are going to have a flexible data set to test how the magnetic microscopy is able to obtain, or how many grains, or the amount of grains it can obtain from different situations, like thin sections with very high density of grains, thin sections with low density of grains, mixing between single domain, vortex, multi-vortex, and multi-domain grains.
Yeah, exciting stuff. Yeah, thanks, Ricardo.
Brendan?
Hi, Ricardo. Really interesting talk. I was wondering, you had on slide 27 a figure, which I think is from that newest paper that's just going to be published.
Yes.
So here you show in this top figure that things that are recorded in the very, very weakest fields, as you increase the number of particles, do not converge to an angular misfit of 0. So for like practical paleomagnetism terms, does this mean that, things that record a very, very weak paleomagnetic field will not record an accurate direction? Why is that angular misfit not going to 0?
Yeah, it's a very interesting observation of this paper. In fact, if the field is too small, it's not enough to flip and orient the magnetic moments. And so it's not a question of not having the ability to show the direction precisely, but also the intensity. So it's a limitation of the method that we are not. What we see is that we start to have something that converges after about 1 microtesla, but below 1 microtesla, it seems that the results are going to provide random results. We are now testing this using rocks and ceramic fragments for very low magnetic fields for the induction in the lab to see if we are able to reproduce those modeling results.
Mm-hmm. But would that apply to bulk rock measurements as well, or is this something that's specific to microscopy?
No, that would be the same for outcrops as well.
Interesting. Thank you.
Richard?
Thanks. Yeah, really interesting talk. While we're on that slide, I wanted to ask, so you're assessing this model using angular misfit.
Yes.
Quite helpfully, I think, finding that you can get good results with relatively small numbers of particles. I just wondered how that compares if you're interested in recovering paleo intensities. So can you similarly get away with a few thousand particles if the field intensities are similar strength, sort of 10 to 50 microtesla?
We think so, Richard. We think it's possible also to obtain paleo intensity from a small amount of particles as well. So that's something that's not covered in this paper. We mostly worked on the ability to provide the direction. Mm-hmm. But we also think that it's possible to obtain a paleo intensity from a much smaller amount of grains than it was supposed in the Burns paper.
And what's the main reason for the difference between those two papers? Is it just the way that you're treating the vortex state magnetization? Is that the key thing?
That's one thing. For example, in the Burns paper, a grain had only 2 options, up and down. Mm-hmm. And here we have considered all the options for the orientation of the magnetic moments inside the grain and alignment to the field. So this is much more powerful when you compare to the up and down possibility. But also a Burned paper, they used the alpha 95 parameter to evaluate the quality of the matching between the orientation and the average of the magnetic moments. And this is very strongly dependent on the number of grains. So we think it's a major drawback of that paper. So that's why we use the angular misfit.
Okay, thank you. Great.
Okay, Gunther has a talk. It says, nice talk, thank you. In your slide 28, you have 2-3 millimeters scale across. Does it mean that the anomalies that are detected comes from mostly multi-domain grains?
Oh, the anomaly, the magnetic anomaly is much, much bigger than the grain itself. The magnetic anomaly is, that is created by a grain is much larger in surface than the grain that's generating that anomaly. So yes, the resolution of the magnetic microscope is not at the nanoscale, but we are able through the magnetic field that grain generates define the magnetic moment of the grain that is much, much smaller than the anomaly itself.
Johan?
Hi, Ricardo.
Hi, Johan.
Great work coming out of your lab. I have a question actually about modeling hysteresis loops. I was wondering if you considered the mineral hematite, since, and correct me if I'm wrong, some of the low temperature data you showed suggested the presence of hematite. So, have you
Oh,
tried
low
that
temperature.
to include in your models?
Okay. Yeah, the low temperature showed Besnus very way, in fact. I don't know if I'm. It's the interpretation is that we didn't have hematite in those rocks.
Yeah, there's that slight drop, I guess between 200 and 250.
Yeah, you're talking about
Mhm. Yeah,
yeah,
maybe
about
that's the
here.
more in
Yeah,
transition.
we didn't put hematite as part of the assembly.
Okay, thank you.
But thank you very much, Johan.
Okay. I guess there are no more questions. So we thank Ricardo again. Thank you very much.
Thank you all for being here, and then I think we have lots of things to do in this domain, and also in collaboration for the use of those techniques. And I invite you all to use our series.
Just before ending the session, I wanted to share one more slide. So our next speaker will be on April 2nd, and you can check all our talks. They are uploaded to YouTube. So now we can start the on-record session.